Okay, good evening. Sir Deems here. So I'll be discussing thermodynamics. Um, First, let's define what is thermodynamics. It comes from two words, thermo and dynamics. Well, as you see, thermodynamics is the branch of physics that deals with the conversion from one to another of various forms of energy and how these affects temperature, pressure, volume, mechanical action, and work. And as I've said earlier, it came from two Greek words, therme and dynamis, which means heat and power. So therme and dynamis is the root word of the thermodynamics. But basically, when you define thermodynamics, you're technically saying that it's about heat and power. Okay. So it was first used in the publication by Lord Kelvin. Original name was William Thomson. He uses that term thermodynamics from his publication. And the first thermodynamic textbook was written by William Rankine in 1859. Remember, these names are the reason why we consider the absolute temperature in the units of Kelvin and Rankine. Okay, so the, these are the people who contributed a lot in terms of thermodynamics. Continuing, we are discussing about the system. So a thermodynamic system is, uh, or simply a system refers to a definite quantity of matter, most often contained within some closed surface chosen for study. So basically, we have three parts in a system. We have the system itself, we have the boundary, and the surroundings. Okay. So the system, the boundary, this is the surroundings. Then let's discuss the kinds of thermodynamic system. These are actually asked in the board exam, but seldom there are I mean, usually they were asked, but um, the quantity of or the frequency that they are asked is not that frequent. Okay. So they usually ask one in every four board exam, but it's still good to understand about these kind of thermodynamic system. So first we have the closed system, also known as the control mass. Uh, Basically, the reason why it was called control mass or the closed system because we don't have an opening, but um, energy can enter and leave, but mass cannot enter and leave. That's why we're controlling the mass. So it's a system consisting of a fixed amount of mass and no mass can cross its boundary. So no mass can enter or leave a closed system. However, energy in the form of heat or work can cross the boundary. Like for example, you have an egg and you boil an egg. So basically, heat can transfer within that system and it will be absorbed the within the system and the egg will be boiled. But there will be no mass that can enter or leave through that system. I just give an example of an egg, but an egg is not a system. I just want you to visualize about how closed system works. Okay. Just remember it known as the control mass and energy can enter or leave the system. The next type of system or the next kind of system is open system. Well, this time mass can enter and leave. So we cannot say that it's control mass, but it actually controls the volume. So if mass enters and if the volume of the system is already full, some part of it will leave the system. Okay, if you add more mass, some part will be removed. So technically, you're controlling the volume and not the mass. In this type of system, energy can also enter um, with the addition of mass also. We can enter the energy or even energy itself without the addition of mass. But again, for the open system, we're not controlling the mass, we're controlling the volume. Okay. Next, isolated system is an ideal system in which neither mass nor energy is allowed to cross the boundary. So isolated, it's like it's really an ideal system wherein no energy can cross also. Remember that in a closed system, energy can still enter, but this time isolated system um, cannot allow the energy to enter. Okay, so those are the three kinds: so closed, an open, and an isolated system. Now let's discuss about property. I guess we already have this kind of discussion in chemistry, but let's define more of what is a property is. So it's a quantity which serves to describe a system. It can be divided into two general types, and these are intensive and extensive. So what are the difference between intensive and extensive? Intensive is one in which does not depend on the mass of the system. So, for example, color or temperature, those are intensive property. However, extensive property is one which depends on the mass of the system. Like for example, the momentum or the kinetic energy or the potential energy. Those properties or those type of um, property are known as the extensive because they really depend on the mass of the system. Then we go to these temperature scale. So what's the temperature? So it's a measure of the intensity of heat of the substance. The first unit that we can consider is the most popular, which is Celsius scale. It was named after Anders Celsius, also known as the SI unit, and the freezing and boiling points are assigned to 0 and 100 degrees Celsius, respectively. So what are these points? Well, basically, if the temperature of the water reaches 0, after the 0, the water will freeze. That's your freezing point. It's also the part where from ice, when it becomes 0 degrees Celsius and you're heating it, it's increasing in temperature. So the point where it changes from ice to water is also 0 degrees Celsius. That's why we call it the freezing point. The boiling point, on the other hand, is 100 degrees Celsius, wherein it's the temperature when you reach the temperature of 100 for water, the water will boil and can be converted into steam as well. Okay. Now for the next unit, we have the Fahrenheit scale, or it's an English system, named after um the I mean maybe he is a scientist or his name is Gabriel Daniel Fahrenheit. Okay, so later I will show you how to convert from degrees Celsius to Fahrenheit, but for now let's consider the freezing and boiling points are 32 and 212 degrees Fahrenheit respectively. These are also the same as 0 and 100 degrees Celsius. They're just converted into their Fahrenheit equivalent. Next unit of temperature is the Kelvin. wherein we're now converting it to an absolute temperature scale. So it was named after Lord Kelvin, but his real name was Sir William Thomson. Um, there's a story where it was changed into Kelvin. I'm not really sure how the story ends or how the story went, but they used to tell us a story about he there's a king or that changes his name from Sir William Thomson to Lord Kelvin. I'm not really sure if that's true, but you can search that out. Okay. So later I will show you how to convert the temperature from degrees Celsius to Kelvin because this is also an SI unit of system. Then the last one is the Rankine, which is also the English system of temperature, wherein it's an absolute temperature as well. And then there's also conversion from direct from degrees Fahrenheit to Rankine. So when you're using an English system, it's better to use Rankine and Fahrenheit. And if it's in SI, you need to use Celsius and degree Kelvin. And here are the units of or conversion formulas that we need to consider when we want to convert from Fahrenheit to Celsius or vice versa, and Celsius to Kelvin and vice versa. So if you want to have conversion from Kelvin to Rankine, you need to convert Kelvin to degrees Celsius first, and then from degrees Celsius to Fahrenheit, then Fahrenheit to degree Rankine. Okay, so remember that when you want to convert Celsius to Kelvin, you just add for 273. And for a Rankine from a given Fahrenheit, you need to add 460. Again, these are absolute temperature. Okay. So why do we need to consider absolute temperature? Because when we're computing later on the gas laws, when you divide the temperature and you consider it as in terms of Celsius, like for example, the temperature is in the freezing point, which is zero. If you don't use the absolute temperature, dividing a zero means an infinite value. So we need to consider dividing it in terms of its absolute temperature so that we don't actually get a unit or a math error when we're computing gas loss. Okay. For uh, in order to convert Fahrenheit to Celsius, you need to subtract first. So you need to simplify first the parentheses. Subtract 32 from the degree Fahrenheit. Then afterwards, you multiply it by 5 divided by 9. And vice versa, well, like for example, you are given the Celsius and you want to convert it to Fahrenheit. So you need to multiply first the 9 over 5 and then you add 32. Okay. So in your calculator, you also have the conversion unit, like convert, not sure what the number is, but I guess it's 38. Yeah, there you go. So for example, you have 40 degrees Celsius to Fahrenheit. That's 104 degree Fahrenheit. Okay, if you're gonna use the formula, that's a 40 degrees Celsius to Fahrenheit. So 40, you multiply first the 9 over 5 before you add 30. Okay, so that's a similar answer we have. Okay, so just remember to use whether your formula, you memorize it, or if you forgot it, guys, there's also a conversion on your calculator. Now, let's discuss properties. So the first property is mass density. The mass density of a material is defined as the mass per unit volume. Okay. We know about density, it's about mass over volume, but basically there are two types of density here. We have the mass density and the weight density. The difference between the two is that we are referencing weight density in terms of its weight. So you need to multiply the gravity from the given mass in order to convert it to weight. Because basically the formula, if you want to convert mass into weight, just multiply it with the unit of gravity or the constant value, which is 9.8066, or sometimes we use 9.81 meter per second square, or in other contexts, they're using 9.8. Worst is they approximate it to 10, but that's a lot approximation when you want to use it. So I'd rather consider the 9.8 rather than the 10. Okay, but the exact value is, I guess, it's around 9.8066. So now we have the specific volume. So the specific volume is the reverse of the density. That's a volume over mass. The unit is volume per unit mass, okay, or the reciprocal of the density. Specific gravity, on the other hand, is, or relative density of a substance, is the ratio of the density of the substance to the density of some standard substance. When we say standard substance, like for example, we're using liquid. So we'll be using density of the water when we're comparing specific gravity of liquid. Like for example, you want to compare the specific gravity of liquid such as mercury, although mercury is not technically a liquid, but you see it's the form of mercury is like liquid in nature. So when you get the specific gravity of that, or um, if you want to understand what's the specific gravity of the mercury, it's basically the density of the mercury over the density of the water. Okay. If you want to consider the specific gravity of gas, like for example, um, helium, you may want to consider the standard substance, which is air, which is in 1.2 kilogram per meter cube. These are standard values that you need to memorize. So another standard is usually water at 4 degrees Celsius for liquids and solids, while gases is it's usually air. Oh, I actually mentioned that one. But the values are 1,000 kilogram per meter cube and 1.2 kilogram per meter cube. So what does it say? You need to consider that the density of water is around 1,000 kilogram per meter cube. So I have some sort of analysis of how I memorize this one. Like for example, you have a 1 meter, a box of 1 meter by 1 meter by 1 meter. You know how long is your 1 by 1 meter, right? It's like the length of your shoulder from the tip of your hand. So that's how long it is. Now, from this part, this is, let's say, for example, 1 meter and then 1 meter, and then the height is 1 meter. So imagine this box is really big. And when you pour a lot of water in it, okay, you pour a lot of water in a 1 by 1 by 1 meter, you basically imagining that the weight of the water here is 1,000 kilograms. That's how I analyze it. Okay. Now, if the same scenario is you change that water into air, air is lighter compared to water, but air, since we're living in Earth with a lot of air or oxygen, there's still a weight of air when you enclose it in a 1 meter cube box. Okay, so that weight is considered as 1.2 kilogram. And say, for example, you have a weightless box that can contain water or that can contain air, then you carry that box that will weigh around 1.2 kilograms without the weight of the box. I guess, because I just mentioned that consider a weightless box. Okay. So the air here is now 1.2 kilograms. That's why we have the density is means that 1.2 kilogram in every 1 meter cube. Or if there's a water, that's a thousand kilograms in every meter cube. I hope you consider those values because that's how I memorize these two constants here. Next, pressure. Pressure is defined as the force per unit area. Okay, we usually consider um, pressure in terms of the force and in terms of area. Well, in strength of materials, this is always discussed because pressure literally equates to the strength or the stress. Okay. So when we say, like, for example, you want to build a house and then you build, what you call this, a column, or this is the foundation of your house. Okay. Usually they place around something like this. It's the bottommost of your foundation wherein they consider a large area here. Why do you think we have the large area? Because pressure is literally in terms of force over area. So when you increase this area, it's inversely proportional. So basically the pressure now decreases. So even though if you have a lot of force that can apply in your foundation, that will not equate to a lot of pressure because of a larger area. So imagine that this is an area with a very small foundation. I mean, then this is your post, okay, something like this. So with this smaller area, the pressure here now is much higher compared to this one, which has a higher area. Okay. So that's how I analyze your pressure. And it basically has a unit of Newton per meter square. And that unit is equivalent to Pascal. So remember that. The unit of Newton per meter square is Pascal. I remember when I was in college, my teacher told me about a story where Newton and Einstein and Pascal are playing hide and seek, and then Newton was standing around a 1 meter square box. So here's Newton. I mean, they play hide and seek. This is Newton. Then Einstein is caught Newton. He said, Newton, that's you. Like, for example, they're playing hide and seek. Einstein caught Newton. Then Newton said, no, I'm not Newton. I'm Pascal because I'm standing in a 1 by 1 meter square. Well, my teacher also told us it's a joke, but I just remember a story about it. I'm not sure if that's a funny one, but let me just move forward about another formula for pressure. So right now, we're not gonna focus ourselves with the force over area for the pressure. We usually consider the density multiplied by gravity and then multiplied by height. So pressure is rho GH. Okay. So rho is the density in kilogram per meter cube. Multiply that to gravity, that will become the weight density. So that will become Newton per meter cube. Multiply that to a height of meter, that will give you a unit of Newton per meter square, which is equivalent to our pressure. Speaking of this pressure now, let's talk about different types of pressure. We have the absolute pressure, the gauge pressure, the atmospheric, and the vacuum pressure. So what are the difference? Absolute pressure is the total pressure exerted on the system. The gauge pressure is the amount by which the absolute pressure exceeds the atmospheric pressure. This is actually how what we measure in a pressure gauge or in in a, let's say for example we have a barometer that used to measure the pressure. So gauge pressure is what we measure, right? But basically the definition here, it's the amount which the absolute pressure exceeds that of the atmospheric pressure. Because atmospheric pressure is constant. It's usually the pressure caused by the weight of the atmosphere. Okay, so it's actually a constant value. When you weigh or when you gauge a pressure and then something is like for example you weigh around 500 Pascal and then your atmospheric pressure is 1 atmosphere. So that 1 atmosphere must be converted to Pascal. Then you add it to your gauge pressure. That will basically equal to your absolute pressure. Now, vacuum pressure is significantly lower than atmospheric pressure. So it's a pressure wherein there's no weight about the atmosphere. So we're gonna convert them later. So here's how it is. The absolute pressure is the atmospheric pressure plus the gauge pressure. And the another formula is absolute pressure is atmospheric pressure minus vacuum pressure. Just remember these formulas. Now, let's talk more about the unit of conversion. So one atmosphere is equivalent to 101,325 Pascal, or that's a 1.013 bar. It's also a unit of pressure. Or in English, they use the 14.7 pounds per inch square, or another unit for 1 atmosphere is 760 millimeters of mercury. Also, it's the same with 760 torr. So you need to memorize these conversion because later on when we have problems like in terms of pressure and they don't have consistent unit, just like my example earlier about 500 Pascal and then 1 atmosphere. So you need to convert those units for you to answer or for you to add or subtract these pressures. Okay. And we have the Pascal principle. This is basically a breakthrough on hydraulics wherein they use the Pascal's principle to to lift a car. They have these fluids here. It says that the pressure 1 is equal to pressure 2 because even if you have apply a very small force, but the area is also small, it can lift a car with a much greater force with a much greater area. Because say for example your force is 10 Newton and your area here is 1 meter square, 1 meter square. So you have basically 10 Newton per 1 meter square, which is 10 Pascal. But it can be equivalent to a force of, let's say, 1,000 Newton car with an area of 100 meters square, something like that. Just an analogy. Because the area there is 100 and your force is around 1,000. So 1,000 over 100. It's the same ratio of your 10 Newton per meter square. Okay? So that's the Pascal's principle. The pressure applied to a confined fluid increases the pressure throughout by the same amount. I mean, that's the area or the ratio. All right, so let's answer few questions before we go to computations. Like, if a metallic object is heated, its density generally, what do you think? So when a metallic object is heated, um, the the object actually expands when it is heated because the increase in temperature will be equivalent to a change in the volume also. Remember a formula like change in length is equal to alpha um, in original length multiplied by change in temperature. So when you increase the temperature, your length also increases. So what happens to the density? There's also, in terms of volume, alpha initial volume change in temperature. So basically, you increase the length, you also increase the volume. So when you increase the volume, you're increasing the um, well, the density is mass per unit volume. Okay? When you increase the volume, what happens to density? It decreases. So I think the answer here is when a metallic object is heated, the density generally decreases. Okay, that's it. Next, who invented the barometer? Remember that it's a device used to measure pressure because of the unit of bar. Okay, so remember bar, like in in the bar exam, they have this hammer, and when you have a hammer, you're speaking about Thor. So it's Torricelli. Okay. It's not a joke. This is how I memorized this one before. So remember that. Bar means Thor or hammer. Okay. That's how I memorize it. Next, the temperature of a gas measures okay, when you have temperature, you have motion in the particle of gas. So when you have motion, it really equivalents to a speed or a velocity. And when you have a velocity, you're technically considering about kinetic energy. So the temperature of the gas measures the average kinetic energy of the particles in the gas. Okay? Now, a specific property is also, um, what do you think? Is it an extensive or intensive? If we recall, extensive is dependent on the mass, and intensive does not depend on the mass. So, specific gravity, like for example, specific gravity. For a specific gravity, this is density over density of standard material, or say, for example, water. So they have a problem here because they say that the density is in terms of mass over volume. This is mass over volume as well. So they said that the specific gravity is dependent to mass. Well, not really dependent to mass because the mass also here will cancel out that mass. So basically, it doesn't depend on mass. And a property that does not depend on mass is an intensive property. Okay, just recall the video or rewind it, go to the definition of property, and you can see there that intensive property does not depend on the mass of the system. Okay, let's compute these problems. A 30-meter vertical column of fluid given density is located at G, wherein G is 9.65, MPa square is meter per second square. Find the pressure at the base of the column. So as you can see, we have this is a direct formula of pressure, wherein pressure is rho, G, and then H. And rho is the density, given the density is 1878 kilogram per meter cube. I usually write the units when I'm solving a problems in thermodynamics because um, when you're aware of the units, you you basically confident, you're basically confident it that your answer is correct or not because you know the equivalent unit. Now, if my problem is pressure, I know that the unit must be in Pascal. So I'm trying to consider the units to make it in terms of Pascal. So this kilogram per meter cube must be converted to or must be multiplied to 9.65 meter per second square. And this will give me kilogram meter per second square, which is equivalent to Newton. Okay, or that's a Newton per meter cube. Now I just need to multiply the height, 30 meter, so that the unit of meter and meter cube will cancel out. It will give me a meter square, and the kilogram meter per second square is Newton. So this is basically a Pascal unit. Okay. And what's the value? 1878 multiplied by 9.65 times 30. So that's a 543,681. The answer, um, that's a 543.68 kilopascal. So I think it's letter D. Okay. Next. On a day when the barometer reads 755 millimeters of mercury, a tire pressure gauge reads 204 kilopascal. The absolute pressure in the tire is what? Okay. So if we recall the formula of the absolute pressure, it's the atmospheric pressure plus the gauge pressure. So what do you think is the atmospheric pressure? That's your measurement from the barometer. That's on the day when the barometer reads 755 millimeters of mercury. That's your basically atmospheric pressure. The pressure gauge of the tire is your gauge pressure 204. And as we can recall, the absolute pressure is atmospheric pressure plus the gauge pressure. Okay. And here's the problem because the atmospheric pressure is at 155 millimeters of mercury. We cannot just simply add this to a gauge pressure, and that gauge pressure is 204 kilopascal. So we need to convert 755 to kilopascal. So how do we convert it? Um, from these values, 755 millimeters of mercury, we need to consider multiplying it to 101,325 Pascal or 101,325, 0.325 kilopascal in every 760 millimeters of mercury. So that your millimeters of mercury will cancel out. And there you have your pressure in terms of kilopascal. So using my calculator, 755 times 101.325 divided by 760, I have now the value of 100.658 or around 100 kilopascal. So when I add this, I'm going to change the 755 to 100 kilopascal. So I just simply have 304 kilopascal, right? And based from the choices, oops, we don't have a 304 kilopascal. So how do we answer this one? Now, I have two more units in terms of meters of mercury. So I can just try to convert this back to millimeters of mercury. So how do I do that? By dividing to 101.325 kilopascal, we're multiplying 760 millimeters of mercury. Now you may ask, so why do you use the millimeters and the choices are in meters? Later we'll just convert it to meters when we have the millimeters. So 100 plus 300 at 204, you have this 304, then, or basically you can just write 304 times 760 over 101.325. You have here 2,280 millimeters of mercury, or this is the same with 2.28 meters of mercury, changing the millimeters to meters by dividing 1,000. So I think that's it. That's a letter D. The decimal error of 0.01 is basically because of we just rounded off 100 kilopascal. I think it should be 100.68. Okay, but that's good enough for this problem, 2.29. Now we go to a rise in temperature of 20 Kelvin is equal to a rise of what? And uh, how do we do this? So they used to convert Kelvin in terms of Celsius by adding 273, but that's actually wrong. You need to add 273 to degrees Celsius to make it Kelvin. So basically, if you have 20 Kelvin here, you need to subtract 273, which is negative 253. But how come we don't have a choices like that? But because the problem here is not the conversion of temperature from Kelvin to Celsius, but rather a rise, or meaning a change. So here's a hint. When you say change in temperature in Kelvin, this is the same with change in temperature in degrees Celsius. How come they're the same? So the answer is 20 degrees Celsius. I know this for a fact because I memorized it before, but basically I also know the concept behind. When you say a rise in temperature of 20 is also a rise of temperature 20 degrees Celsius as well. So how do we do this? Like for example, you have 20 degrees Celsius initially, and it goes up to 40 degrees Celsius. So the change in temperature now in degrees Celsius is 40 minus 20, which is equivalent to 20 degrees Celsius, right? In terms of Kelvin, individual temperature will be converted. So 20 plus 273, and then it will now increase to 40. Then you still add 273. Okay. So what change in temperature then? It's now, it became now from 293 to, it is now changed to 313. And when you get the change in temperature now in Kelvin, that's the 313 minus 293, which will result to 20 degrees. The value is 20 degrees, but the unit now is 20 degrees Kelvin. So a change in temperature, even if it's in absolute, that will be the same with in terms of Celsius. Okay? So I guess I've explained this problem. Now we go to the next problem. The area of thermodynamics concerned with the measuring of thermal properties is called thermal. So basically, when you say thermal, you're measuring about heat or heat energy. And another unit of energy is also calories. So that's why we'll be considering calorimetry here. Okay. And we go to gas law. By the way, after this gas law, we just have a break. I'll just record this, or I'm recording this one. I'll go convert this then upload this again, just like what we did in chemistry. So let's discuss about gas law, then we'll have a break. But what are gas laws? These are a set of laws that describe the relationship between thermodynamic temperature, pressure, and volume of gases. Let's start with Boyle's law. So in Boyle's law, the definition here is at constant temperature, the number of moles and the volume of gas varies inversely with the no, no. The definition here is that at constant temperature and number of moles, the volume of gas varies inversely with the pressure. How come we have this formula? So in terms of Boyle's law, the pressure is inversely proportional to volume. In mathematics, when we want to uh, make this proportionality symbol be changed to equal sign. So when I change this to equal sign, I need to introduce a constant K. So pressure now is K times 1 over V. Now, if I want to compute for K, I need to cross multiply volume. So that will give us pressure times volume is constant. And that constant is the product of pressure and volume. So your pressure 2 is now equal to, or the pressure 2, when you multiply it to volume 2, will be the same as pressure 1 times volume 1. Because constant is considered a constant. Okay, so that's your Boyle's law. Now, for Charles' law, your constant here is pressure. At constant pressure, P is constant. But by the way, here temperature is constant for Boyle's law. Here, Charles' law. Okay, pressure is constant. It says here that the volume is directly proportional to temperature. Okay, that's the definition, I guess. The volume directly proportional to temperature. It means that when you increase the temperature, your volume also increases. In here, it's the other way around. When you increase the volume, the pressure decreases. Okay? So, like when you want to uh derive the formula, you just basically use mathematics as well, then just divide by temperature on the left side. You have um, something like this. V over T is constant, and that's equal to V over T as well. So this will now be your initial value, and these are your final value. Remember that this is Charles' law. Okay, P Charles. And then for Gay-Lussac's law, so Gay-Lussac's law is, for Gay-Lussac's law, your volume is constant. Okay, so they used to they use the concept here that when the volume is constant, the pressure is directly proportional to temperature. So that's the definition of, I guess, Gay-Lussac's law. So the volume is directly proportional to its temperature. So again, by mathematics, you divide temperature on the left side, you have P1 over T1 is now equal to P2 over T2. I want you to consider this one, the combined gas law. Okay. So ideally we have P1 V1 over T1 equal to P2 V2 over T2. How do we consider this one? I actually want you to consider the ideal gas law of PV is equal to nRT so that you won't miss a thing. Like when the temperature is constant, your product of pressure and volume will be constant as well. But when you consider like pressure is constant, your volume is now equal to T, so you need to divide T on the left side. You have V over T, and that's your Prince Charles, or I mean the Charles, or I mean the pressure is constant. Okay. By the way, I mentioned about Prince Charles because I have something like this, mnemonics for the gas law. So for Charles' law, like I mentioned before. For Charles' law, pressure is constant. That's why I have Prince Charles as my mnemonic. For boil, you know what's the meaning of boil, right? When the water is boiling, you're increasing the temperature. So that's why the temperature there is constant. For the Gay-Lussac's law, um, V is Gay-Lussac's law. I'll just memorize that. I don't want you to consider about V being Gay-Lussac or well, it's up to you. How do you memorize that? So now when I move to the ideal gas law, you'll be considering about the combined gas law as well. You just need to divide by temperature here. Your PV over T is PV over T as well. That's N now is just constant. Later on, R, we'll discuss this one. This is the universal gas constant also. So, oh, wait. So this at constant or at standard condition, we have the 0 degrees Celsius, 1 atm pressure, and 22.4 liters of gas. Okay, if you memorize these, this is the condition, or these are the values when the problem states at standard condition. So you need to use 273.15 Kelvin, your 1 atm or 101,325 Pascal. This one is in terms of times 10 raised to 5. And the volume of 1 mole of gas is 22.4 liters. Okay, you need to consider that. Now, for an ideal gas law, as I mentioned earlier, your pressure times volume is equal to the number of moles times the universal gas constant times the temperature. Now you need to memorize the absolute or the universal gas constant wherein we have different values. Like it's a 8.314 joules per mole degree Kelvin, 1.986 BTU per mole degree Rankine, 1545 foot-pound force per mole degree Rankine, and this is my favorite, 0.0821 atm liter per mole degree Kelvin. Okay, if you memorize these values, you won't be having a problem in ideal gas law. But I guess you need to consider that there's also a constant in your calculator that can show you the universal gas constant. I just can't remember the number. I'll try number 27. Okay, that's it. That's your number 27. Luckily, I just used the correct number for the constant. Again, that's shift constant. And then I'm gonna type 2, 7. That's your R, and R is your universal gas constant. This is the exact value, 8.314 or 314,472. Okay. But you can use also 8.314. And then we have the Dalton's law of partial pressure. This is easy because it says that the total pressure of the mixture of an ideal non-reactive gas is the sum of the partial pressures of the component gases. Okay. So like for example, a system is experiencing a pressure from P1, then P2 was added, and then P3 pressure 3 is added. You just take note of all the partial pressures, and when you add those, that's your total pressure. You don't multiply, you just add. Okay? Then the Avogadro's law, it's where your mass has the ratio m1 over m2. So at equal volume, at constant pressure, and at constant temperature, the gas contains the same number of molecules. I remember we used this one in terms of in chemistry. Mass 1 over mass 2 is molecular weight 1 over molecular weight 2. It's also the same with gas constant R1 and R2. Okay, now let's answer this problem before we have our break. The formation of packets of gas in liquid is called what? So it's a question in a board exam wherein you need to consider there are there can be a formation of packets of gas in a liquid. For example, there are bubbles or something like that. The term there is a cavitation. Okay, it's not absorption or dissolving. Just consider checking the definition of these three that are wrong. But cavitation is the formation of packets of gas in liquid. Next, okay, here's the problem. 5 moles of water vapor at 100 degrees Celsius and 1 atm pressure are compressed isobarically to form liquid at 100 degrees Celsius. The process is irreversible and the ideal gas law apply. Aha. There's a problem in the question. We don't have a question. Really, there's no unknown here. But basically from the choices, the unknown value here is the volume, okay? So you need to consider the choices as your hint whenever this problem arises. Okay, so we'll be using the ideal gas law, the PV and RT, and we need to solve for the volume. The formula is nRT over P. Okay, do we have the number of moles? Let's check. We have 5 moles. And temperature is 100. And the pressure is 1 atm. Okay? So this time, if the volume is in liters, I won't be using the 8.3144 because the unit of the volume there is meter cube. Also, the pressure there is in Pascal and not in atmosphere. So I'll be using the constant of 0.0821 atm liter per mole degree Kelvin. Okay? So the number of moles must be multiplied, which is 5 moles. And when you multiply that, mole will cancel. Temperature, okay. It's 100 degrees Celsius, but as you can see, you need to add 273 to make it degree Kelvin. So that Kelvin will cancel as well. Now, this is the easy part. The pressure is 1 atmosphere, so it's an atmospheric pressure. So that ATM will cancel out. So now I can solve for the volume. Okay, that's a 5 times 0.0821 times 100 plus 273. Okay, I need to use parentheses there. So 100 plus 273. And then 1 ATM. 153 unit liters. Around 153 liters. So based from the choices, we have now letter B as our answer. Okay? I hope you don't have any question, but if you do have a question, just write it on the comment section. I'll try to answer them as soon as I read them. Okay? Or you can just message me also. Next, a 3-pound mass of air contained at 25 psi at and 100 degree Fahrenheit, given that the universal gas constant of air in English is 53.35 foot-pound force per pound mass degree Fahrenheit, what is the volume of the container? The same question here, the volume. So I'll be using the formula V is nRT over P. So the number of moles is we don't have, but actually we have the pound mass. So we can also convert this one to M because our R is in terms of mass. So look, I have 53.35 foot-pound force. Foot-pound force per pound mass, degree Fahrenheit. I'm guessing that it should not be in Fahrenheit. It should be in absolute temperature scale because normally the universal gas constant is in absolute temperature. But let's try this one. Maybe we will have an answer there as well. So the temperature is 100 Fahrenheit. So the Fahrenheit will cancel. The 3 pound mass, number of moles is in mass, so I can cancel at mass. And then pressure. The pressure is 25 psi. When you say 25 psi, that's pound per inches squared. So when you multiply this one or divide this one, actually, your inches square will go up and your pound force will cancel out. But your unit of volume is not consistent because the unit of feet inches square, it's not actually a unit of volume. It should be in terms of inches cube or the feet cube. So we need to convert inches square in terms of feet. How do we convert that? In 1 foot, we have 12 inches. In order to cancel the square, you need to square this one also so that your inches square will cancel and you'll have a feet square in your pressure. And when you multiply feet square into feet, that will give you a feet cube. So then from the choices in there are in feet cubes, so I'll just try to use my calculator to solve this one. That's a 3 times, oops, what's that? Okay, so 53.35 times 100 all over 25 times 12 squared. There you have your answer, 4.45. Then again, you don't have that 4.45 from the choices because I think I mentioned this before, that usually the temperature in the universal gas constant is in Rankine. So I need to change this one in terms of Rankine. So this should be in Rankine. There's an error in the problem. So I'm gonna add, okay, not the 273, it should be 460 degree Rankine. So that when you cancel Rankine, you'll be getting now the volume in terms of feet cube. So using my calculator, oops, okay, I'm gonna change that 100 to 100 plus 460. There you have the answer. It's around 24.9 volume, feet cube, 24. Oops, that's letter C, 24.9. Okay. So that there you go, guys. Let's talk about the next one. How many moles of an ideally behaving gas occupy 400 liters at 0.821 atm and 200 degree Kelvin? So moles from the formula of PV equal to nRT, we need to solve for n. So that's why it becomes PV over RT. I usually write most of the time the unit of R so that my units of pressure, volume, and temperature are consistent. So I'm going to write 0.0821 atm liter per mole degree Kelvin. Okay, so it's around 0.0821. The temperature there is 200 Kelvin. So that's a 200 degree Kelvin. That why we can cancel out Kelvin. How many pressure? 0.0821 atmosphere. Or I think that it's only a 0.821 atm. Ah, there you go. It's 0.821. Then 400 liters. The volume is 400 liters. We can cancel the liters. We can cancel atmosphere. Now this mole in the denominator, from the denominator, it will be um, move up to have our unit in terms of moles. Okay, that's a 20. Oh, I didn't compute it yet, so sorry. 0.821 times 400 over 0.0821 times 200 here. I guess it's a 20, really at 20 moles. Okay. So I hope you don't have any question, but if you do have again, just contact me or type it in our chat box or rather the comment section. Next, the total pressure of three gas components in a certain mixture is 55 kilopascal. PA is 20 and PB is 7.5. What is the partial pressure of gas C? This is an easy one, even if it's a board exam question, guys. This is really an easy one. The total pressure is equal to partial pressure A and B and C. Okay? So actually, this is the question, the partial pressure at C, but the given total pressure is 55 kPa, 55 kilopascal. This is now equal to PA is 20 kilopascal, so that's 20 kilopascal plus PB. That's a 7.5, 7.5 kilopascal. I hope you don't um, use the shift solve here of your calculator. Just transpose these value. So if I'm going to use my calculator, it should be 55 minus 20 minus 7.5. That's it. It's around 27.5 also. So the partial pressure at C is now 27.5 kilopascal. This is an easy one because we have a consistent unit, but basically that's how you do it. Okay, next. Oh, now this is in terms of STP, standard temperature pressure. But the question here is not number of moles, but number of molecules. Remember how we count or how Avogadro count the number of molecules? That's why we have the Avogadro's number. If you can still remember that it's constant. Oh, I forgot it again. Constant 24. Okay, that's it. Constant 24. So in every 1 mole, you have 6.02 times 10 raised to 23. So our goal here is to compute for the number of moles first before we compute for the number of molecules. So as we have discussed, the number of moles is PV over RT. And I usually write the 0.0821 atm liter per mole degree Kelvin. Okay? The pressure is at STP. So at STP, you have 1 atm atmosphere. The volume is not at STP, it's given 2.5. 2.5 liters. Well, basically, the 22.4 liters, it's in terms of 1 mole. Well, you can use that also to compute for the number of moles later by just ratio and proportion. But later, I'm going to check it out. And then we don't have the temperature, but the temperature is 0 degrees Celsius, or in terms of Kelvin, it's the 273 degree Kelvin. So that Kelvin will cancel out, liter will cancel, atm will cancel. You have N as the number of moles. So 1 times 2.5 over 0.0821 times 273. It's our 0.1115 moles. Okay, this is not yet the answer, but I want to try by ratio and proportion, as we have mentioned. Oops, my whiteboard closes, sorry. So as I have mentioned earlier, at standard temperature pressure, your number of moles is actually in every 1 mole you have what volume? If you can still remember, it's around 1 mole represents 22.4 liters of volume in gas. So if we want to take the um, the formula for this one, number of moles over volume is number of moles over volume as well, initial and final. Okay, your initial or your final is your 1 mole in 22.4 liters. Okay, and the number of moles initially over volume 1, this can be multiplied to the right side, so volume will be multiplied here, so that your unit of moles here divided by this is in liters. The volume given is around, based from the problem, it's at 2.5 liters. So that's a 2.5 liters. Canceling liters, let's check whether it's still the same. Okay, let's try to use one more calculator. But in the board exam, it's not allowed, okay? So when I do something like 2.5 over 22.4, oops, there you go. It's almost the same, 1116. So that's good enough, I hope. So that's a number of, you don't need to use the constant value of at STP. So this value now will be multiplied to the number of molecules, because the number of molecules is now number of moles times Avogadro's number. So 0.1115 moles, multiply that to 6.02 times 10 to the power of 23 molecules per mole. So that mole will cancel. You only have in terms of molecules. Okay. So I have here multiplied by constant 24, or the Avogadro's number. Okay. That's a 6.71 times 10 raised to 22. 6.7 times 10 to the power of 22. I guess our answer here is letter D. Yeah, there you go. Next. Okay. So this empty space here represents our break. So I'll be stopping here for now. We'll have a break and then continue it later. Or basically, I don't need to have a break since it's a recorded one. But for me to upload this in an easy manner, I need to cut this down to 2 videos. Okay? So that's it. Thank you very much for now, and we'll see you later.